So there are mainly four kinds of transformation we have to learn. The translation, in which the graph is shifted horizontally or vertically. The second transformation is dilation, in which the graph can be shrinked or can be elongated. The third kind of transformation is flipping of the graph. It means the reflection of the graph about a particular line. And the fourth one is the rotation of the graph. We will learn all these transformation on any random function, that how the transformation will work, what kind of algebraic addition or operation we will do into the x or maybe the entire function, and we will see what will be the pictorial effect of those kind of operation employed over any function. So that will be the random graph we will see, but also it's important to understand that what kind of transformation will be happening on any known function, what we actually know in our syllabus. So like suppose I have a function of sine x or the graph of sine x. If I apply any transformational algebraic operation on that, how the graph will shift or maybe shrinked or maybe elongated. So before that, I will give the idea about what are the basic functions we should know to understand this kind of transformation better. So the first basic function I want you to learn is the identity function. I think you know that. So the first is identity function. So identity function is a function defined as fx is equal to x. Suppose you have f1, it means it will give you 1. So whatever value you are putting inside the function, it will spit it the same thing as the result. So the domain, if I'm talking about, so domain is all the values of x which satisfy the function. So domain is going to be all real number, because there is no such a real number we cannot substitute at the place of x in the function. And for the range is also real number, because whatever you substitute, you are getting the same thing. So whatever will be the domain, that will be the range. And the graph of this function will look like the line y is equal to x. It's not look like, it's exactly the same. So this is the line y is equal to x, and this represents the function fx is equal to x, and that is identity function. The second function, the second kind of function, I want you to notice that is a quadratic function. And the quadratic function, if I say, is generally not the general quadratic function I'm talking about. Like if you know that I have a function fx is equal to ax squared plus bx plus c, where all a, b, c are real numbers, and of course this a cannot be 0, then this function can, otherwise the function will become linear. So I'm talking about the pure quadratic function in which the x square term is only present, not the linear part of the function. So if I have the function fx is equal to x squared is a pure function, pure quadratic, and the graph of this pure quadratic will be the upside open parabola. So this is the graph of fx is equal to x squared. It is why so, because if I substitute the value of x as 1, that will give you 1. At negative 1, it will also give you 1. So at 1, this value is 1. At negative 1 also it is 1. At 2, it will go up to the 4, and at minus 2 is 4. This graph is not that much accurate graph because I'm drawing by hand. So I have to take some other points there to draw the graph perfectly. but you have to understand this is the graph. This is the nature of the graph of the fx is equal to x square. So what is the qualitative kind of observation you can do? The first observation, you can see that the graph is the y is equal to x square, or maybe fx is equal to x square. If I say this graph is symmetrical about x-axis, sorry, y-axis, symmetrical about y-axis. And when I'm saying that symmetrical about y-axis, it means that if I take this y-axis as the line, the right part of the graph and the left part of the graph are symmetrical about each other. It means the y-axis is acting as a mirror, and the right part is symmetrical or just like the left part, and so on. The other way to think this symmetrical thing is this way is, if I say that, suppose I'm going right towards right from the origin, let's say 1 unit, and whatever height we get at 1, the same height we get if you go backward from the y-axis. It simply means that if I'm moving x unit away towards right from the y-axis, the value of the function, whatever I get, I will get the same value at negative x. And this is the feature, or this is the nature of the function, what we call it the even function. So this kind of function in which fx is equal to minus f of minus x happens, we call it even function. One thing also you can understand, that the range of the function, range is all the values taken by the function on the y-axis. You can see that no value is taken below the x-axis. It means the values on the y-axis they are taking is all the real number, but all the real number are positive. So we can say that all are positive, or more precisely we have to write in the interval from 0 to infinity. The domain at the same time, you can say domain is real number because there is no such restriction given. So it is entire x-axis value it is taking up. So this is the fx is equal to x square, is a pure quadratic. And this kind of basic graph you must know. Then only you will understand the transformation accurately. Although there are some other techniques to draw the graph of any quadratic by using the nature of roots and all those kind of things. But here we will learn only the transformational effect. Now this third kind of function I want to say, that is a cubic function. So fx is equal to x cubed, and you can see that the graph of this x cubed is like this, because at -1 the graph the value of the function is -1, and at 1 the value of the function is 1. So the graph will pass through -1 in the third quadrant, and will pass through 1, 1 in the first quadrant, and the function will behave like this graphically. This is fx is equal to x cubed, and this is the observation we can say here, that this fx is equal to x cubed is symmetrical about origin, and the point we can say the origin. What is the meaning of that? If we are moving, let's say 1 unit right to the origin, we are getting the height 1, but when we move leftward by the same unit, or the left to the y-axis, we will get the same depth. So we are going 2 unit right, we get the height 2, height 8, but if we get 2 unit left, we will get depth 8. So this is the meaning of symmetry about the origin. And so what is happening by this observation is the value at x is negative of the value at minus x. And so this kind of function is called the odd function. And this will be also helpful sometimes to draw the graph. So if you observe the odd function we have here, it will be helpful. Now comes rational function. And in rational functions, the basic graph I want to convey of and convey the nature of is 1 by x, where this x cannot be 0, and it is actually known as the rectangular hyperbola, whose graph is like this. All these graphs you need to understand or know to understand the graphical transformation better. You come to know what is my point sooner or later, but you have to just be persistent. Okay, now this is rational function. And what about the domain range? So for this, domain is all real number, because there is no such real number we cannot put except one number is 0, which we have already taken here. And the range is, you can notice that again the range is not taking the 0 value. So again real number except 0. Here one thing also I just forgot to tell you about the cubic function. The domain is all real number and the range is again all real number. Rational function, the basic rational function, we will have this thing. Now comes exponential one. So all the graphs of exponential function will be the same as I am drawing the graph of y is equal to e to the power x, where e is 2.718 ... and you can notice this graph will be always positive because the domain is real number, but the range is always positive. And means always positive means non-zero. So let me just write in this way, that will be better, 0 to infinity. So you can see that when I'm taking any negative number also it will give you positive quantity, and the graph will look like this. It will shoots up infinitely when you go higher positive values for. Now this point is 0, 1, because at 0 the value is 1. So this must you have the graph sense for this e to the power x. The next is the logarithmic function. So for logarithmic function, if you have learned the function chapter better, you know that the logarithmic function is the inverse of the exponential function. A logarithmic function, I mean to say the base is e only, and this graph will look like this. This is y is equal to ln x. Ln x means, sorry, this is 1, 0. At 1 the value of log will be 0, so this will be 1, 0, and this base is here e. So I mean to say that this is log base ex. If you talk about the domain for this function, so you can see that domain is always 0 to infinity, but the range is all real numbers because you can take any value from y-axis. Now there is one trigonometric function also you should know. I'm just going to give you the idea what kind of transformational effect will happen on this trigonometric function, and when we just learn the trigonometric function in detail, then we will learn all the transformation in each of those trigonometric functions. But here you should at least get some idea about the transformation on at least one trigonometric function. So that's why I'm taking the sin x function for this learning, and the sin x function will be a periodic function. The period is 2 pi, so 0 to pi, this kind of nature of the graph will be there, and pi to again 2 pi, the inverted nature will be there, and again it will repeat its behavior after this. This is pi by 2 and this is 3 pi by 2. So these are 7 kind of function on which I will try to give my transformation, and we'll see that how this kind of graphs will get changed too. So now we will learn what are those transformations and what is the effect, but for that I will take some general function or general random graph. So the first graphical transformation we are going to learn is translations, and in translations basically there are 4 kind of translations: the shift rightward, shift leftward, shift upward, and shift downward. So how this kind of transformation will be get to, or how this kind of translations will happen, and what kind of algebraic changes we do in the function to get the effect of these translations, we will have to see. So the thing is, if I say that translation, it can be also seen as or said as shifting of the function, or shifting okay, shifting of the graph or graph of the function. And in this, the very important thing to notice is, we will see that here. Let us first understand what is the meaning. So suppose I'm taking any random function like this, and what will happen, suppose I have this function like this, and this is the general function I will take for every kind of explanation, every transformation explanation. So here I am taking origin, and this is -1 here, and so on. So this is the function I have, and you want to get the shift. And what kind of shift I want to go? Suppose I have this as y is equal to fx. So I have the first kind of shift I want to give the horizontal right. So suppose you have y is equal to fx, and the other function I'm writing y is equal to f of x plus, let's say x minus k first. The second kind of thing can happen, y is equal to f of x plus k. Then third kind of thing you can say y is equal to fx plus k, and the fourth kind of thing you can say that y is equal to fx minus k. You see that in the first two kind of transformations, I'm adding k to the x. So here what is the thing you have to understand? The k is added. Let me change the color. K is added, and I'm saying added, it means the algebraic added, means it can be added or subtracted. Anything can happen. Let me write it. Now k is added, or let's say subtracted also. I'm writing subtracted to or from x. You notice here I'm saying that this thing I have to mention that k must be positive. So k is positive, and I'm adding or subtracting. So this will give you the effect of, what kind of effect this will give you? So the first f of x minus k will give you the effect of shifting the graph rightward k unit. F of x plus k will give you the effect of shifting the graph leftward k unit. And why it is happening, let us try to understand. The idea is this: suppose I have the function fx given in this way, and I want to find a new function which is f of x minus k. So previously you can see this thing, what is happening. At 0 the value of the function is 0. By observing this graph you can see. Now ask yourself that if I have the change happen to the function from inside, that f of x minus k, what x will make you the f of 0 is equal to 0 kind of behavior once again? Means at what value of x the value of y will become again 0. So you notice that the original function here was giving the value of y 0 at x equals to 0. It means that this x minus k must be 0 to get again this y 0. And where this x minus k will become 0? When I substitute x equals to k. It means this kind of behavior will be exhibited by the function, the new function, at k is equal to 0, means at k comma 0. It means this entire point, this point will be shifted to k. But the similar kind of behavior will be shown by each piece of the graph, or each part of the graph, or each point on the graph. Therefore the entire function or entire graph will be shifted to k unit rightward. In the same way, suppose you have x plus k, it means you have to ask yourself that at what value of x the y value will become 0, so that it will be exhibit this kind of nature. It means I have value x equals to minus k, and where is minus k on this whole picture on the x-axis? It is right left to the origin k unit. It means the entire graph will be shifted k unit leftward. It means, let's try to draw the graph. So suppose you want to draw the graph of the first part, x minus k. It means, let us say I have this k. I don't know how much I have taken this thing. It means this part will be shifted here. And now if this is 1 comma 1, now it will be k unit this side. So I don't know what will happen, but you notice that this is the similar kind of behavior will be shown. Now this will come k unit this side, and now the graph will be like this. So this is, it means what you are observing, that each piece of graph or each point of the graph will be shifted k unit ahead, and this is f of x minus k. So the red graph I have drawn is f of x minus k. So this was k unit rightward shift. In the same way, what will happen if I want to say the k unit leftward shift? This entire graph will be shifted leftward. It means this piece will go k unit that side. So I'm just taking here somewhere the value k. So let's say this is k here. So I want to say minus k comma 0 because k is always positive I'm taking. So what will happen? Again I have to draw a parallel line to this line here, and the origin point we have to shift here. So the graph will look like that, and on this piece it will go this side and then that side. So let me draw it. It will look like something like this. And here what is happening, that you have shifted this entire graph k unit back. I don't know, because I want to give you the difference. So I'm not taking this k, right, left k or right k are the same magnitude. I'm just giving you the idea how to shift. So this is the kind of shifting you observe. This is coming from that part and so on, and this is coming from this part. So every piece of the graph will be shifted k unit left. So when I'm adding any value k from inside, it means I'm adding any value k to the x, the graph will be shifted horizontally. If the k is positive when you are actually adding, it means the graph will shift left. When the k is positive when you're subtracting this thing from x, the graph will be shifted right. Now if I have these two to understand what is this thing. So this is going to be f of x plus k. It means when we are adding k from the outside, the graph should shift up, and we are adding the or subtracting the k from outside, the graph will shift down. So it is actually k is added or subtracted from or to whatever to fx. This whole thing can be understood in this way, that it is just y minus k is equal to fx, and this is y plus k is equal to fx. So this is also, you can make the analogy. What is the analogy you can make from here? That in this two scenario we have added and subtracted the k value from x, and here we are adding and subtracting the k value from y. But it's a little bit weird to think in that direction. We can also, we always try to think in that way, because we are adding some k to the fx or subtracting that k from the fx. So what will be the effect of this thing? The graph will shift up when we are adding, the graph will shift down when we are subtracting. So let me draw the graph once again. Okay, so this was the original function I had, and I want to draw the graph of fx plus k. So fx plus k means the graph will shift up 1 unit. It means this was suppose a minus 1 comma 1. Fx plus k means graph will shift k unit, not 1 unit. So this will become 0 comma k, and a similar kind of behavior will be shown. It means it will go like this somewhere, and again like this somewhere. Alright, so this is the shifting up, you can see, and this is the effect we are observing by this first y minus k is equal to fx. And same, if we are drawing the graph, we want to draw the graph k unit down, the graph will be shifted at 0 comma minus k, and again I'm not taking the 0 k and the k magnitude same on both directions. So this will give you similar kind of behavior here, and here we have shifted the graph k unit down. So this is the effect we observe. This is translation actually. So you notice now what is the summary of this whole thing. Whenever we are adding a k from inside, that is we are adding a k from to x or subtract for the k from x, the graph will shift horizontally. When we are adding the k or subtract the k from outside, that is we are adding or subtracting in fx, the graph will shift vertically. Alright, and in whole thing, this whole process, what is the key observation? I want to write it here. The key observation is, this is the key, that the shape of the graph is not changing. Shape remains same. Means shape remains, there is no deformation or that kind of thing. Whatever the exact figure you are taking from the origin, you are only shifting that thing, and whatever the function you have to keep the similar kind of graph when we are shifting the graph, and that's why it's only shifting. It's not like any changing. Now comes the next kind of transformation, that is the dilation. And dilation broadly means that we are changing the figure, and there are again 4 kinds of dilation. So just let me just write it. So broadly we can say there are 2 kinds of dilations: a shrink in the graph and a stretch in the graph, or this is compression in the graph, you can say, and elongation. I'm not writing, so you understand. So shrink can happen. Either the vertical shrink can happen. Vertical shrink means the graph will shrink like this. If the graph given, it will be shrink like this. And there's a horizontal shrink also. So it can be like this. So this I am calling is vertical shrink. And this is a horizontal shrink. Similarly, the stretch can happen in two ways. Either you can stretch the graph vertically, or you can stretch the graph horizontally. So there are four kind of dilations can happen, and you can now observe, or you can also figure it out, that whenever the shrink and stretch will happen, the graph will get deformed. It means the shape of the graph will change. Shape of graph will change. For that, let me just take another random curve, and I will give you the idea of what is the effect algebraically we can observe here. Suppose I have this kind of graph given. To make you understand the shrink and compression, that will be a good example. Suppose this value is 2 here, this value is 3 here. This is 3, by the way, not 2, that's correct, and this is -1. I want to understand the, first of all, vertical shrink and the vertical compression, the vertical stretch. So for that, let's do this kind of transformation. Suppose you have this graph is y is equal to fx, and I want to draw the graph of y is equal to kfx. Not kfx, yes, kfx. You see that originally the function value was 0, correct? At 0. This was y0 because f0 is 0. Do you think that if I change this kind of transformation, or do this kind of transformation in the function, or we multiply algebraically the function, the value k from outside, do you think that the 0 value at 0 will change? Of course not, because we have multiplied this k, the f0 is still 0, and the k will not give this any change. It means that this point will be always there. Whatever the value of k is there, if you do this kind of multiplication, this point is always there. Again, you see that since f0 is 0 and also f3 is 0, at 3 again the value is 0. On this function also, the f3 is 0. It means these 2 points will never be changed. But think what will happen to the other values. It means that the value at 2 for the previous function is what? The value at 2 was 1. But when we are doing the similar kind of calculation here, means in this function, now at 2, this will give you the value k times 2, k times f2, correct? So k times f2 means what? At 2, now the value of the function will be shoots up k times, it will go k times higher, but provided the value of k is what? If the value of k is lesser than 1, then it will go down, means the value of f2 will be not be shoots up, it will go down, it will not be increased, it will be decreased. So it depends upon the value of k. So let's assume that first here the value of k is 1, greater than 1. If the value of k is greater than 1, the graph of the function, I'm just drawing for this scenario, the first scenario when k is greater than 1, and I'm drawing in, let's say, this color different, let's say this one. So at 0 there is no such change, but at 2 it will go to k unit. It means it will go like this, but at 3 again it has to come down, so it will come to the 3 again at the same point. What will happen this side? This side also, if you take any value here, suppose I'm taking any value, if you can just see that this here I'm taking, the previous value is here, but now since we have multiplied k and the k value is bit more than 1, it means the graph will drop down, because it should exhibit the higher negative value. It means our graph will come down, and at -1 it will give you the minus of, the -1, it will give you the k times the value of -1. So this is the graph you have seen. It is actually giving you the vertical stretch. So what is the key takeaway from here? The takeaway from here is, whenever I am multiplying the k from the outside and k is more than 1, there is a vertical stretch. The vertical stretch means this kind of thing is happening. It's not shifting, it's only stretching. So as if you have to understand that at the x-axis someone has pinned up the graph. Wherever the graph was hitting the x-axis, we have pinned up. So this point is pinned up here, and again we are stretching the graph like this. So this kind of behavior is exhibited by the graph when k is more than 1. Now what will happen if I take the second scenario? And the second scenario I am taking for k is lying between 0 and 1. So when k is lying between 0 and 1, you can see that now the value at 2 will be now 1 by k. It means whatever the value we have, it will be diminished by k factor, because now the value of k is 0 to 1. It means now the graph will be like this, what was originally drawn. So in this side it will go down, it will come like this, and again it will hit 3, because at the x-axis points is already pinned up, and on the left side of the origin we have to go lesser negative value, because now the k value is 0 to 1, so this will come like this. So this is the graph we have, and this you can observe that we have given the shrink into the graph, because we are shrinking and the entire graph is deformed. The original graph is not preserved anymore, because we have pinned up the graph on the x-axis and we are only stretching some part, or maybe we are compressing some parts. So this is the kind of dilation we will observe when we multiply k from outside. So when we multiply k from outside to the function, there is a vertical shrink or the vertical stretch. The vertical stretch will happen when k is greater than 1. The vertical shrink will happen when k is lying between 0 and 1. Now I am taking the same graph to understand what will be the effect if I multiply k from inside. So I want to observe this kind of changes. The first is y is equal to f of kx, and what is the effect we will observe? So try to think, how do we think this thing? You see that at 0, and again there is no such changes will happen, because this is originally y is equal to fx, and at 0 still will give you 0, because this k times 0 will be 0. But at 3 what will happen? You can see that originally the value of the function at 3 was 0. So the same effect the graph will exhibit at k by 3. So because this was a kx, and when I substitute x equals to k by 3 by k, not k by 3, it will give you 3, means the value of the function will become 0 again. It means the graph will be compressed by k unit. So suppose previously it was hitting the 0 at 3 here. Now it should hit that thing at 3 by k. So this will become 3 by k comma 0, and the graph should be compressed like this. Let me draw it, and it should give you the value 1 at somewhere here 2 by k, and it will go to take the value 1 there. It will come down and hit the x-axis again. So this is actually happening, the horizontal shrink. And this side also you can feel the same kind of behavior. The left hand side of the horizon will have the same kind of behavior. The graph will shift towards the horizon. So because it was originally at -1, it will give you the value -1. Because you multiplied, so the same effect you should observe at -1 by k. But this horizontal shrink will be exhibited by the graph if k is greater than 1. And you can notice that if the k is greater than 1, I have horizontal shrink. But if I have k less than 1 and more than 0, between 0 to 1, the same kx, f of kx, will give you the horizontal stretch. It means this time, if you want to draw the graph, previously the function value, the black graph is exhibiting this kind of behavior from here to here. At 3 it was give you 0. Now it will give you the same value at 3k, because the value is lying between 0 and 1. So the meaning is that suppose I am dividing by any number. Let's say k is always greater than 1, and here I am just dividing by k. So in that case, what will happen? Automatically the value we have multiplied to x is lying between 0 and 1. So let us keep this k greater than 1 always, and it will be better to understand in this way. So if k is greater than 1, and I'm saying that for this effect, I mean the previous one, there is the same shrink will happen. But when we are dividing a number which is more than 1 to the x, it will give you the effect as if we are multiplying a number which is lying between 0 and 1 to x. And this time what will happen? There is a horizontal stretch. This kind of behavior will be shown by the function. And so you notice now, what is the key idea or the key takeaway? That whenever we are multiplying a number which is more than 1 to x, there is a horizontal shrink. Whenever we are multiplying a number, dividing by a number which is more than 1 to x, then there is again horizontal stretch. When we are multiplying a number which is more than 1 to a function from the outside, there is a vertical stretch, otherwise it's a horizontal stretch. Otherwise a vertical compression or vertical shrink. Alright, but what will happen if I take k is equal to -1 in this whole scenario? Let's try to understand. K is equal to -1 here, and here the function was y is equal to fx first. And I want to say that y is equal to k of fx, but k is equal to -1. It means it will turn into y is equal to minus of fx. So if y is equal to minus of fx, what will happen? It will happen like this. Try to think, whatever the value of the fx was previously providing you at the value of x, that whole values will be negative of the previous value. It means that at 2 originally it was giving the value 1, now at 2 it will give you the value -1. At 3 whatever value it was giving, this remains same because 0, but some other parts whatever value we are getting here, it will turn to the negative of it. At here it will turn into negative of it. The here it will turn to negative of it, and so on. We have to think. It means the entire graph will be flipped about the x-axis. So negative portion will go to the positive portion, and the positive portion will go to the negative portion, and so on. So this is the graph, the flipped graph, and this is the graph of y is equal to minus of fx. So when we are multiplying a minus sign from outside of the function, there is a horizontal flip, a vertical flip, sorry. There is a vertical flip. So vertical flip is also, I can say that is the reflection of each piece or each portion in x-axis. It's not like where we have to take whatever we see, we have to take the reflection. It means if the graph is positive side, we have to take negative side. The graph is either negative side, we have to take the positive side. So better to understand the flip word, because we are flipping, we are taking each reflection. And you can now notice that what will happen if I have f of minus x. So for f of minus x, what we will do, let's see. So if I have f of minus x to draw from y is equal to fx, try to think in this way. What will happen? If I substitute x equals to 2 now, it should give you the value. Let's see. Originally the value at 2 was 1. But at minus 2, if I take this in this function, at x equals to minus 2, I am substituting here. What will happen? It will become f of minus 2, and that will give you f of 2. It means that whatever the positive value you have taken, at that positive value, the function will act as if it is taking the negative value. So for all these positive parts, means towards the right of the y-axis, it will go leftward, and all this negative part will come rightward. It means there is now the vertical horizontal flip, means we are flipping horizontally. It means the new graph should look like that. At negative 2, it should give you the value 1, and at negative 3, it should give you the value 0. And this portion will go this side. And this is the graph of f of minus x. You can check it also, because now at 2, the value is not defined, means value is not given there, because if you put 2, it will act as a f of minus 2. And at minus 1, it will act as a 1. At 1, it will act as a minus 1. And at 3, it will act as a f of minus 3. But at minus 3, it will act as a 3. Therefore, that minus 3, the value is 0. So if you are multiplying the minus 1 to the x from inside of f of minus x, there is a horizontal flip, sorry. It also means that we are taking the symmetrical, the mirror image of the graph inside the y-axis. The next is the rotation, which we are not going to cover this thing. The rotation needs some other kind of technique, so we will focus on that rotation in the last parts of this video series. how the rotation will happen. The rotation means for that we have to change the axis and see how the axis change will give the effect to the rotation of the function. So this thing I'm not going to touch here. Now we'll see that all these basic functions, how they are exhibiting their behavior, how the shift is happening in the GeoGebra. So let's go to the GeoGebra. So here we are in GeoGebra. So for that I'm going to give the value k as a slider. So k, I'm hitting it and it will give you a slider value. I want to make this k positive so that our assumption is consistent. So I'm taking this positive and I'm always showing you the value 0 to 5, and it will be sufficient to understand all the transformations. I'm taking the function fx and I'm calling it for the first time x, and I'm going to apply all the transformations on it. So for that I'm writing the second function as fx plus k that must show you that the graph is shifted k unit above. And the second function I'm taking, fx minus k, it means it must shift your graph k unit down. The next is I have to show f of kx, and this is f kx, and there is a value of k is 1 there, so that's why there's no change you can observe, and I think that's okay. After that there's no such thing we have to show. So see, I'm going to change this fx here one by one, and then we will see how the translation or all the shifting is happening. You can see the value of k is here 1. I'm going to mute this all the other two, and this fx is equal to k. I'm going to change the value of k from 1 to above till 5. You can see the graph is shifting above as we are going higher and higher value for k. Okay, now we go for any value lesser than k, lesser than 1, it is also going lower, and at 0 there no shift is happening, so it will behave as a gx only. But same thing we can see if I'm taking k is equal to negative, it means the graph should shift below the x-axis, because k I'm always taking positive, so I'm going to give the value k higher than 0, so the graph shifted down, because now the minus sign is acting as a minus sign because k is a positive value. So you can observe that what is happening in this thing when k is subtracted from the function, the graph will shift downward. For this fx is equal to x. And for the same thing, if I take fx is equal to kx and I'm giving the value more than 1, the graph is now stretched vertically. But I'm giving the value less than 1, the graph is compressed vertically. To understand this thing in other graph, let us just change this value of the function. So I'm calling this fx is equal to x squared, and let's try to observe whole scenario one thing, and one go. So I'm just changing this all, just taking all these things and I'm changing the values of k. So you can see that the blue graph, there is fx minus x. It means the graph should shift k unit. The orange graph is a graph shifted 2.2 unit, but this gray graph is giving you 2.2x, means the dilation is happening there. So you can see that what is the effect of k on it. In the same way, suppose I'm taking the x cube graph and try to understand all the dilations or the shifting. So this is one way you can think that these two graphs here and here, let me change this color so that you can see that a little bit difference. This one deeper and this one is also one. Let us change, yeah, that's okay. So I change this gray to some other teal. So now you can see that this dilation is happening, but these two are shifting is happening. When I go to the less than 1, so for less than 1 the shift will be different, but you can say dilation is now stretched, means. So I just mute these two things, the teal graph, you can observe what will happen. For k less than 1, the value you are multiplying to the x from inside, there is a dilation or the stretch horizontally. Alright, for this other function, let's try to understand. Suppose I am taking a function e the power x. So for e the power x, I have this kind of scenario happen, and you can see also the shift and the vertical and vertical shift. Also you can observe in all the graphs horizontal shift. How do we change it? If I just take f of x plus k and f of x minus k, the similar observations you can do. So that I think it's cluttered, so I just mute something like this. I disable, so you can see this thing. You see the horizontal shift, and also this will give you the vertical shift. Now suppose I try to draw the graph of log x and try to see what will happen. Ln x. So this is here, and these are horizontal shifts you are seeing. And suppose you want to change this thing, you can see that as soon as I go for the higher values of k, and k I am taking is a x plus k. So when we are adding the value of k from inside, the graph should shift left, and so on. There is one more function. There is 1 by x. Let's try to think how it will happen. So this is 1 by x here, and for each you can see this kind of observation by just changing the values of k. So in this way we can understand everything visually in the GeoGebra. If you want to play with that, it is the tutorial for you. You can just re-watch it and see how I have created all these pieces. Now let's do one question from the scratch. How do we apply all the transformations on that? Now let us try to draw the graph of y is equal to twice of x minus 3 the whole square plus 1. So to draw it, first of all we have to identify what is the basic graph it is coming from. So the basic graph we have to understand that is y is equal to x squared. From there I need to draw the x minus 3 the whole square first. From there I am multiplying this 2 from outside, and from there I am adding this 1 from outside. So this whole effect we have to understand from this x square graph from the basic. So I have, let us say, the fx is equal to x square like this. I am drawing the schematic, not on the scale, because the grid is so high in size, and that's why the graph will be a little bit giant. That's why I'm taking the small graph to understand everything. So suppose you have this x square graph. At 1 this is 1, and so on. So first of all, x minus 3 the whole square, it means the graph I have to shift 3 units rightward. So let's say this is 1, this is 2, this is 3. So I've shifted the entire graph 3 units rightward. Let's say this is 2, so at 2 the value of the function is, for this is now 1 only, so it will become here, and so on. So this is the graph of the second part, second transformation. Now the twice of x minus 3 the whole square, it means the graph will be because you're multiplying this 2 from outside, so the graph has a stretch. How do we understand this dilation or the stretch from the outside? We have to understand that if I have at 2, previous the height was this one, but when we are multiplying this 2 from outside, at 2 it will be twofold of the previous value. It means that 2 only, the graph will be the higher than the previous value. Therefore the graph should look like this, and you can see that is a vertical, a stretch twofold. So this will be now the new graph, that is the second transformation, and it will be like a vertical stretch. So this is third, this is second, no, this is the first one transformation, this is the second transformation. And now after this you're adding 1. It means the entire graph will be shifted 1 unit. This is easy. We can shift the entire graph 1 unit above. So that will be graph, and we are shifting. We have to preserve the previous shape of the graph. So there are no such kind of changes. So you can observe that in all the shifted portion of the graph, the shifted transformation of the graph, this graph is the previous graph. We have shifted, there is no such shape change. But whenever we are doing a dilation, it means we are shrinking or stretching, then only the shape is changed. And again after the change, we are shifting the graph, so then there is no change in the previous one. So in this way we can understand the transformation, we can apply the transformation, and there are many such questions can be done on the basis of transformation. So this was the first lesson of this whole transformation of the graph deeper dive series. So upcoming videos are more in detail, and this was just the basic, and in the next video we will understand the modulus function, and also understand that how do we apply the modulus transformation. It means we apply the modulus function, or we do the composition of modulus function to other function, what kind of effect we will observe. See you in the next video. Till then, stay math active.